So we're into chapter 14, solutions. So we've done solids, liquids, gases. Spent quite a bit of time on that in the last few chapters. And now what we're going to be doing is talking about mixtures, homogeneous mixtures. So if you remember, the definition of a solution is a homogeneous mixture. And that means it's got two or more pure substances combined in such a way that it's uniform throughout. So no matter where you sample it, the properties or the constitution or composition will always be the same. All right, so what makes up a solution? There's two parts to a solution.
So the solute is what's being dissolved, and the solvent is the thing that does the dissolving. It's kind of a odd definition, but you'll understand when we talk about how many types of solutions there are. But let's say we take sodium chloride and we put it in water, and then you stir it around, all right? The solvent would be the water, and that's the thing dissolving the sodium chloride, which is the solute. In solutions that involve a solid and a liquid, or a gas in a liquid, so we're talking about this situation here, the liquid is always the solvent. But when you're dealing with mixtures of gases, for example, like air, right? Air is approximately 80% nitrogen. This is the mole percent, if you remember that. 20% oxygen, and it's actually, there's some argon in there too, but we'll ignore that for now. But if you had that mixture, then what do you call the solvent, right? So what they normally say is it's whatever is the majority component, whichever you have the most of. And so in this case, this would be nitrogen would be the solvent, and O2 would be the solute. There's all kinds of solutions though. Many of them people don't think about. Air, people generally think about. Liquid solutions though, like vodka or bourbon or scotch or anything like those are actually solutions of ethyl alcohol and water, like they've listed here. So it's a liquid solution. You can also have gas liquid solutions. For example, a soda has carbon dioxide dissolved in the water, and that's why the bubbles appear to come out of the water. It's really the oxygen, or the CO2, sort of precipitating out as a gas, as it were. And then there are solid solutions as well. So alloys are really homogeneous mixtures of two metals or two elements, and so an alloy is a type of solution. There's a lot of terms, and my encouragement to you is, for this chapter, if you haven't been doing it, you should be going to the end of the chapter and looking at the important terms and writing out those definitions, and then keeping them handy and going over them periodically, so the language of this chapter becomes familiar to you. So let's go ahead and go over some of the terms that are important and generally apply to most solutions. So there's something that we call the solubility limit. And the solubility limit is how much of a solute you can dissolve in a solvent. And there are different ways to do solubility limits, but one of the most standard ways is to say a quantity of solute in a quantity of solvent. So this is not like the mass of the solution, this is actually the mass of the solvent. Solubility limits can be done other ways too. They can be done for liquids, for example, but typically the way we're most commonly thinking about them is grams and grams. But for liquids, sometimes they're done in volumes, okay? And sometimes they mix, they use masses and volumes. So you have to be careful and make sure you understand what the solubility limit is referring to. Okay, so in this example, solubility is the quantity of solute that will dissolve in a solvent. So it says how many grams of alum can be dissolved in 95 grams of water. So the solubility limit of alum is 1.7 grams per 25 grams of water. So you can calculate grams of alum, and you notice I didn't write the formula. You don't need to know it. I'll write it out for you in here in a second. But grams of alum will be equal 95.0 grams of water times, and then the solubility limit is 1.7 grams for every 25.0 grams of water. And you do that calculation, what you'll end up with is something like 6.46 grams of alum. So that's the maximum amount of alum that you can get into water at 6 degrees Celsius. Now, I should also point out, though, an interesting thing about solubility limit. If you want to make a solution that is at the solubility limit in a particular solvent, the way that it's made typically is simply by continuously dissolving material into a given amount of water until the solid stops dissolving, and then you know you're at the solubility limit. Okay, here's another question. How many grams of alum are dissolved in 95 grams of saturated solution? So this is a little bit trickier of a question because 95 grams of saturated solution refers to the solvent and the solute. Okay, the solution is both components. So again, it's very important to think about what the terms mean. And so if you want to figure out how many grams of alum are in 95 grams of saturated solution, you have to think about how to use these two numbers. What this gives us is it gives us the ratio of solute to solvent, that's for sure. But you can also rewrite that as 1.70 grams for every 1.70 grams plus 25.0 grams. This represents the mass of the solution of a saturated solution. And this is my mass of solute. Okay, so now what I can use is this is my conversion between grams of solvent, a solution, to grams of solute. So I'm starting with 95 grams of saturated alum, and then I'm multiplying that by, and it's 1.70 grams of alum for every, and then 20, that gives me 26.7 grams of solution. And by the way, solution often gets abbreviated SOLN, like that. So let's see, where do I have solution? Yeah, this word by itself is often abbreviated SOLN. So if I do that calculation, see the grams of alum solution and the grams of solution will cancel out, and what that'll leave me with is 6.05 grams of alum in that solution. So the thing to be careful of in these questions, again, is pay attention to whether or not what you're being given in terms of solution, solvent, or solute, and then determine how you can find by unit cancellation the quantity that you're looking for. By the way, alum is this compound, K2AlSO4 2.12H2O. It's one of the really common compounds that's actually used for like retaining moisture in things, and also for other interesting use for alum is if you have a cut and you rub it on the cut, it constricts the blood vessels and stops it from bleeding. Okay, so But again, in these kinds of questions, the actual identity of the compound is often not that important. It's really important that you understand grams and then what these numbers are representing in the question. Okay, so when we're talking about solubility, there's three important terms to understand relative to the solubility limit. When a solution is below the solubility limit, it means that you can dissolve more material into it, right? Because solubility limit means it's at the maximum amount. So the term that we use for that is unsaturated. So I'm going to have a couple of quick videos that you can sort of watch here.
When nickel chloride is added to water, it dissolves readily. Because more nickel chloride could be dissolved in this solution, the solution is called unsaturated.
So unsaturated solution you can dissolve more in. So generally the observation that tells you a solution is unsaturated, and I don't know if you noticed how much they put into that solution, it's quite a bit. So we would think that nickel chloride has a high solubility limit, okay? But when you add some crystals, they'll continue to dissolve. Another important factor in solutions too is, we'll talk about this later, the solutions, because they're homogeneous, and we've talked about this before, I guess, will be clear. And the way you detect the clarity typically in a solution is by shining a light through it and looking for scattering of light. So one of the very common ways to do that is to shine a laser through it. And if you shine a laser through a solution, the laser remains in its tightly focused beam. But if there are solids dissolved, little particles that aren't dissolved, what you'll notice when you do that is you'll see scattering of light, that is the spreading of the laser's beam as it goes through the solution. This is actually known as the Tyndall effect, and Tyndall is one of the guys who actually, if you've taken like an ecology or biology class, you might have heard that name before, because he used this technique to determine scattering of light in mist. So where it gets its name, and it also did stuff with like greenhouse gases several hundred years ago. Anyways, so that's called the Tyndall effect, that allows us to tell using a laser or a bright light to see that a solution is actually a solution, that the solution is clear. Okay, so the next term is saturated, and that means a solution that is at its solubility limit. So when you have a saturated solution, how do you know, right, that it's at its solubility limit? Well, one way is to just add crystals to it, and crystals will no longer dissolve in it. But the other way that we know that we have a saturated solution is when we do a precipitation reaction. So if you take two clear solutions, let's say, I'm going to make myself a little space here, I'll write it all the way out here. Two clear solutions, and you mix them together, and then that solution becomes cloudy, right? That's a precipitation reaction, if you remember that from earlier. Well, it turns out when it's precipitating, it's coming out of the solution, and it forms because it can't dissolve, that by definition means it's at its solubility limit, and that's what we call a saturated solution. So here's a demonstration of that.
When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
So this solution that's in here, so this is a precipitation. Again, maybe don't remember this, abbreviated PPT, right? Precipitation, but the solution is saturated. And that's why solid forms. It can't dissolve into the solution. General observations is that it comes from precipitation reaction, and the other one is, the simple one is, if you try to dissolve crystals and they don't dissolve, then it's saturated and at its solubility limit. Now, supersaturated solutions have more solid dissolved than the solubility limit. So that sounds like that can't be right, because right, if it's at its solubility limit, I just told you that's the most you can dissolve. But the trick is, in the definition of supersaturated, it's above the solubility limit, but it's not a stable solution. Saturated solutions are stable, that is, the concentration doesn't change, but in a supersaturated solution, they will eventually precipitate out. So supersaturated solutions are unstable, and they will eventually precipitate out. Now, that doesn't mean it's going to happen right away, but it just means that it can happen. So let's go ahead and watch this video.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid. Some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
So I hope you sort of saw what happened there. There is a little bit of liquid that's left in here, okay? And that liquid is essentially like this liquid. There's a precipitation reaction that took place here, but it didn't start until they poured them on some crystals that were already on the surface. The other way you can get these crystals to form, oddly enough, is you can sort of hit the glass, and oftentimes that'll cause precipitation to take place. The actual trigger for precipitation is very difficult to explain and understand, but the simple thing is if there are some crystals or even dust in the solution, that can cause the crystals to precipitate out. So you have a supersaturated solution is when you add some crystals, then you can get the more crystals to precipitate out of the solution. And then what you're left with is the precipitate and a saturated solution. So this solution that's down here is saturated. Now, there's one more term that doesn't go along with the solubility limit, but this actually turns out to be a good place to put it. Not everything has a solubility limit. Some things you can dissolve in each other in any proportions. And examples are, for example, alcohol and water. You can have as little as 1% alcohol in water, or you could have as much as 99% alcohol in water, in which case you actually have 1% of water in alcohol. But some substances can mix in any proportions, and that's the definition of miscible substances. There are also substances that don't make solutions at any concentration, and those are called immiscible, I-M, then M-I-S-C-I-B-L-E. Okay, so miscible and immiscible solutions. Terms are terms that go along with things that make solutions in any and don't make solutions, any proportions and none. Okay, so you probably already know this, but if you take sugar and you put it in water, right, you can dissolve it to a certain point. And if you wanted to get more sugar into the water, typically what you do is you heat the solution. And so it turns out solubility can be very strongly temperature dependent. And this creates something called solubility curves. So here are some solubility curves for ionic compounds in water. And you'll notice how these are done as they're done as grams of solute in 100 grams of water. Okay. So what are the general trends that you see? Well, if you're looking at it, most substances increase. Right? So that means their solubilities increase with temperature. So for example, sodium chloride, it almost looks like potassium chloride and sodium chloride almost look like straight lines, right? But if you look at something like calcium chloride, it's very strongly dependent on temperature. It goes all the way, and they just basically stopped graphing it, but it goes way up here. So sodium nitrate and potassium nitrate are also both very strongly temperature dependent. And in chemistry, Chem 1B, we'll actually learn about like what are the factors that determine whether or not solubility go up or down. But sodium sulfate is also very commonly used in solutions, but its solubility will go down as the temperature increases. Okay, so most substances increase with temperature change. And the other thing to just make note of, they kind of go together, is that some, not all, but some decrease with temperature. But by far, the most of them increase. And this is actually true for both ionic and covalent compounds. And it also depends on the solvent. So this kind of solubility behavior would be different in a different solvent. So let's go ahead and see how you read this chart, and then we'll use one of the numbers in the calculations. It says, what is the solubility of potassium chlorate at 55 degrees Celsius? So potassium chlorate, we would go to about here, right? There's 55, and you would run it up to this point here. Now this line is 20, but it's just a little bit above, so it's about 21 or 22, right? Let's just call it 21. And then what does that mean? That means that's the number of grams of KClO3 that would dissolve in 100 grams of water. So if you had that much, that would be a saturated solution. Now here's the next question. It says a KClO3 potassium chlorate solution contains 3.5 grams and 25 milliliters of water at 55 degrees Celsius. Is the solution saturated, right? Unsaturated, saturated, or supersaturated? So in order to figure that out, we have to convert this over to per 100 grams. And that's pretty easily done by saying if you had 100 grams of water, we could use 3.5 grams for every 25 grams of water. And we would assume in this instance, because it's water, the density is about 1.0 grams per milliliter. And so I would have a total of 14.0 or 14 sig figs grams of KClO3. And that would be per 100 grams of water. So I use the concentration that's stated and the quantity of water that's used in the solubility to convert that over to mass of potassium chlorate. So now if I'm looking at 55 degrees and I'm looking at 14, it's below the solubility curve. And so below the solubility curve represents unsaturated. If I was above the curve, right, up here, this would be supersaturated. And then the solubility curve represents a saturated solution. And this is true for all these solubility curves, whether or not you're above, below, or on the line for that given temperature determines whether or not you're unsaturated, saturated, or supersaturated. So the last of the terms that goes along with solubility, and actually I should say the last of the introductory terms. There'll be more actually later. There's a lot of terms in this chapter, that's why I'm encouraging you to sort of write them all down. Is the idea of that saturated solutions are in a dynamic equilibrium. And I've mentioned equilibrium before. Dynamic is actually the term that always goes along with it. But what I wanted to do is sort of express to you what that means for a solid in the solution. Okay, so imagine that you had a solid and the solubility is 12. That is 12 spheres dissolved in solution at any one time, and these represent the particles of the solution. This arrow, when things go up away from the solid, means it's being dissolved, and we call that dissolution. It's going into solution. And then the opposite process of dissolution, you already know, going this way is precipitation. So you reach dynamic equilibrium when the rate of dissolution equals the rate of precipitation. That is, how fast it's dissolving equals how fast it's precipitating. Okay, so let's go back to the very beginning here. At time 0, you have a solid and you add a liquid to it. And let's say this volume, it could be a liter for that matter, right? Initially, it hasn't dissolved yet. And so you have a rate of dissolution going on, but you can't have a rate of precipitation because there's nothing in the solution to precipitate. Now, let's say we go to some time later, and that eventually what happens is you actually have, now I've drawn 6 in here, I think, yeah, 6 particles in here. So now you have a rate of precipitation that's about half the rate of dissolution because we're halfway to the solubility limit. Eventually you get to the solubility limit, and what happens at that point is the rate of dissolution and rate of precipitation are the same. So actually what's going on over here is even though the solid in the solution remains the same, that is the same concentration, the crystal on the inside will continue to change its shape. So you can actually, and I've done this experiment before, taken a crystal and I put it inside a saturated solution. So you know that it's not going to get any lighter because the rate of dissolution and the rate of precipitation are the same, and the crystal will change its shape over a course of weeks. Okay, so how long does it take? Well, it turns out when we're talking about equilibrium, some stuff can dissolve fast and some stuff can dissolve slowly, and there are different things that control that. We can talk about that on the next slide, but there are different things that control how fast it dissolves. But it turns out dynamic equilibrium always reaches the same point at the same temperature. So if I started with this solution and I have 1 liter in here, right, and I allow it to dissolve, it reaches dynamic equilibrium at a certain time, and there'll always be 12 of these in the solution. Now let's say I take twice as much solution, and you can see there's way more than 12 down here. So I take 2 liters of solution. Well, what'll happen is it'll take longer for it to hit equilibrium, but there will still be 12 particles per liter of solution, just that I'll have twice as much solution. So there's a lot of things that affect how fast it goes, but it will always hit the same point in terms of its solubility limit. Okay, so once you've reached this, we term this the solubility limit. Okay, so what affects how fast a solid can dissolve? And we'll talk about that next.